So yeah. So our first question is like search suggestion system. So we are given an array of string products and a search word is given. Now we have to design a system that suggests at most 3 product names from the product after each character of the search word is typed. Okay. And our suggested product should have a common prefix with the search word. And if there are more than 3 products with a common prefix, return the 3 lexicographically minimum products. And you have to return the list of suggested products after each character of the search word. Like with mouse, first 2 character is matching with mobile, money pot, and then monitor. Right?
No, I think the first, very first one, they are taking the very first letter.
Oh, it's
That
only
is what I'm
M.
thinking. Yeah, yeah, just the M.
Okay.
And then all of them fall in that, and therefore, if you
Yeah, yeah,
sort
yeah, yeah.
them, that is what
Because
I think. Yeah, but
you are correct, you are correct. Because here M is same, here MO is same in all the, and here MOU is same, and
uh,
here MOUS is same in all the words, and here complete word itself
right,
is same.
yeah,
Yeah,
makes
you
sense.
make
Have
sense.
to start with the whole.
Session, like
Yeah.
what is the question? I don't get that question properly. Will you please explain that?
It's like when you type something on the Google search bar, right? You get a lot, or Amazon e-commerce site, you go, you type some product, black shirt or something, whatever, blah blah. You get a lot of recommendation, right? White shirt, or I mean, somewhat similar to that product. So that is what they're saying. When you type this mouse in your search bar, you will get these as a recommendation. Why? Because this first M is matching, so they might show you top 10 letters starting with M, depending on the probability. Then MO, they'll show words with starting with MO, MOU, and so on and so forth till the end of the string. Auto suggest recommendations.
Okay, okay.
Yeah.
How are we grouping them? Like M should is not there in the output.
No, first letter M is here, right? We check all the words,
We
which
don't
all
take
words are.
into consideration.
Oh yeah, mobile we are taking, money pot we are taking, monitor we are taking, not the mouse is not taking because mouse is already there, right? A
Uh,
monitor is,
No, mouse, no, any word should be there. So as long as they are in the product, they should be a part of our answer,
yeah,
correct?
yeah.
oh, they have mentioned 3 only, that's why.
Yeah, yeah.
3.
So therefore, so you sort all of them, and whatever are the lexicographically first ones, they that only those only are you going to pick, right?
Okay,
Yeah,
okay.
yeah.
Yeah. So
Every
mouse might be.
iteration. So first M. So you'll have like five elements in the list, and each element will have three output
Need
maximum.
not be at max it will be
Or
3,
less.
but so at first glance looks like try if we use put the words in the try, right?
Yeah, yeah.
Yeah, they say like the auto type head and all those, right? Auto suggestions. They
Yeah.
use try, but uh, can we use other than try? Because if someone doesn't know try, you should always have an option in case of try is very specific data structure, which only not
That's true.
everyone, it's common with everyone, right? So if it's not, then we can always go with try. But sure, we'll go there, but we should,
Then
right? Mhm.
yeah. Then normal we have to simulate like go through each of the letters of the what you say this
Right. Yeah,
mouse,
yeah.
right? And
Yeah.
then take those words and
So
sort them
exactly
and
what we were discussing, right? First, we when we are actually typing, if we just
Mhm.
type M, so
Yeah.
as soon as we type M, we go to the products array, we sort all of them,
Mhm.
and take the first M, first three of that value M. We start with M,
Yeah.
right? And then if
Yeah.
we type MO, again you sort the whole products array based on MO. So you just take only those elements which are a part of MO, but in this case, all of them.
Mhm.
Right. So then if you go to MOU, at the time it's only MOU and MO mouse and mouse pad. Those are the only two. So then if you sort them, mouse will always come before mouse pad. Yeah.
Sounds familiar.
Right. So that can be also a reasonable solution, right?
Yeah.
Isn't this a brute force though?
Yeah. It's a
Uh,
you are simulating. It's not a brute. I mean, what they are saying you are doing. That's it, right?
right. No, but it can be a brute force, correct? But we can
But
actually,
is sorting this. So will it be
right.
a brute? Yeah.
No, so you sort them, and then optimize it on its search. Correct. So you
Okay.
can use something, because if it's a sorted array, so then you can actually optimize it to just find those that particular prefix, right? Because this is a prefix now. So
Exactly.
where that prefix begins, yeah. And from there you count number of 3. So you can use a binary search.
Search. Oh,
Right.
that's great. Yeah.
Binary
Very-
search.
Yeah, yeah, yeah.
Right, right. So that is one option, and that's in the solution also, and it works perfectly fine if you use binary search. And it also gives, in some cases, it gives a better time complexity per lead code than try also.
What? How is the approach with binary search?
Well, you sort all the products array initially. That is what you do, and then whenever you are forming a prefix each and every time, you take that prefix and do a binary search on the your products array.
Okay,
So
then.
you will always get an index which from which the first prefix starts with,
Mm-hmm.
using a binary search. So like the lower bound.
So all the prefixes, all the but on the left, oh, like we get that range of start and end.
Right. So on the left will be all the values which are not at all in the prefix, but on the right, from that index, everything will be with the prefix. And so just take the first 3. At least I won't say all of them, but at least your prefix starts from that index. So you still have to look for each and every word when it becomes a part of your answer, whether it satisfies the prefix condition. Right. Yeah, that is also
You
one
may not,
continuation.
right? On the right, there will be a specific range only which will satisfy it.
Right. So if you look at the third one in this output, you see mouse and mouse pad. So other words, there might be some other words after that also, but they are not taken into consideration because we look for the MOU. In this case, MOU is the prefix. So we'll go through each and every word and see if MOU is a part of your word. Then only you take that. Rest
Yeah,
of the part on the right side also are rejected.
but in this example, we don't have like, for
Right,
example,
right.
have like more words which are not matching that prefix, then we'll have it on the right if it's higher end. Otherwise, on the left, we'll have it.
Right. So if you have something like a zebra here, so that won't come because that doesn't match at all any of the
But it
prefix.
will be on the right side of
It will
the.
be on the right side, yeah.
So you'll calculate the ASCII code, something like that.
You just compare the prefix.
I
Okay.
think in binary search, like half of the part will be eliminated all the time, right?
Mm-hmm.
Yes.
So in binary search, that elements can be either in the middle as well.
Yeah. So we'll start from that now. So you do a binary search. Okay. You get an index from where your prefix starts. Right. So from
Okay.
there you start counting if you have a prefix in that word. You take that a part of your output and always look for the prefix. If it's not there, then you stop. So either you
Okay.
keep
Okay.
counting for the first 3, or you count if they are in the prefix. If they are in the if they are not in the prefix and you are still not meeting your criteria of 3, you still stop. So you take the minimum of that.
Okay. Okay.
I think there's some chat. Someone has a question. Devansh, right? Yeah. Did I
I
spell
totally.
it right?
Yeah, you can speak. It's like
Yeah, you
first
can ask
minute.
any doubts, clarifications.
If you want to add anything, go ahead.
I guess we have one more approach. We can generate all prefixes and keep in hash map.
Mm-hmm. That.
It's like
But
traverse. Yeah, please go ahead.
yeah, but only problem there is like if M is the prefix, then entire dictionary will come. I mean, the length of one value will be very large, right?
Yeah.
So
But still,
that
that is a solution, correct?
yeah, that makes sense. And
So
again, you sort them right
Nick, what
inside.
you are saying is you start with M, you push all the words which are matching with that.
Yeah.
Okay. And then, yeah, MO.
You will be sorting every this year, right? All the keys, I mean value, and keep only 3 values to optimize it, right?
Okay, you can do it there itself, right? Yeah, that also makes sense.
Yeah, I am thinking to traverse from each word and so I am taking word mobile. Yeah, I am the first five character is M. Put into to map to hash map and add mobile to list. Then MO. Yeah, put MO to hash map and add mobile to list and etc. Traverse from each word, make a prefix, put in for each word, just that hash map.
It's like he's forcing towards try only. I mean,
Right. So
is
that
it?
was that we used to do earlier also, right? Because if you are not using try, then
Yeah,
exactly that is the approach we are following. And yeah, we just now we are getting more what you say like bias towards try as well as looking at the problem statement. We are trying to create an approach that way. But I think what Nick says makes more sense, right? So you
exactly.
should look for the product values and then put them in the prefix map. So that is a good way because right now we are just focusing on the search word mouse. What if our search words were more than that? Right. So this our approach won't really work. It's not a generic approach or it's not a more scalable approach, right?
Zebra, if they put one more search word, right?
Right.
So
Yeah.
yeah. Even Google uses in search engine try only, right?
Yeah. Yeah. So that is obvious. That is the best way to use. Absolutely. And it's more space efficient also. Because if you look for a larger dictionary, then it makes more sense. But we
Sense.
are actually focusing on only on this search word over here, a single one. So our approaches are slightly biased towards the problem statement, right? Yeah.
You want to share, Nick, that approach? Think not audible.
Sorry, I did not.
Okay, okay.
Okay. No
Yeah,
problem.
this is like the one what I'm having is the normal one. I mean, we are just simulating whatever we have said. This is the suggest. I mean, I'm making a list, going through the each character of your search word, and every time like picking one character, two character, three character, right? Like first I'll pick mouse in my substring as, and now here I'll generate all the possible words which starts with this particular substring, and then I'll sort it and pick the topmost. It's a brute force only, you can say, right?
Mm-hmm. Okay, so you're actually creating the prefix, which you're doing on line number 6.
Six,
Okay.
yes,
Mm. And then
and
going through the products array and then getting all of them.
it's not optimized, I think.
So the time complexity is O of n square log n for this.
It will be n log n every time you are sorting every result, right? So n into n square log n, you are correct.
Not n square, the n into m log n, the search word length into m log n.
That is what n square log n, right? N into n log n is.
Uh,
Actually, it is a word length as well as the product's length.
yeah.
Okay, this is the length of the word. Okay, word length
No, no,
into,
no, sorry. Yeah, it is your search word length only.
so this is a
So that
w
is
And
O of
n
and
log m.
m. And then products we are iterating
whatever
right in result.
w cross n log n, right? Something like this.
Yeah.
Like
And
for
then
every prefix, let's say you got 10 words or whatever the length of the list is, you are sorting every time, right?
Mm.
So worst case, like if everything comes in your here, like if I take n, then everything will come in my list, right?
Mm.
And so in that case, it will be n log n. So w into n log n.
Yeah. So yeah,
W.
your this solution actually is perfect. Only thing is what you can do slight optimization is outside this for loop. You could actually sort these products. Okay. If you sort the products, you don't have to go through each and every word, right? So the way you are actually looking for substring
Mm.
and then you are comparing them and again resorting on line 8, instead of that, if you would have sorted all of them outside, you can avoid the sorting on line number 8, correct?
Oh, before, I mean, you are saying on the original list only you want to sort.
Right, right, right. If you
Okay.
just sort it outside of this, so then that will actually give you a slight optimization. That won't make much of a difference also, but a bit of more optimization.
Actually, that result is RES is outside the for loop only.
No, it's inside.
Oh no, 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 it's inside.
So I sorted the product outside, then go through each of the character.
Then you'll
But
have to update the result, right?
result will be fine, no problem. I think it should work.
But suggested words is what?
So you have
Suggested words like
apply
only sorted words will come here, right?
Okay.
The words are already sorted, and I'll just pick 3 out of
But I
top.
don't see the result RES on line 10.
RES.
You'll have to make
Oh,
it result.
so yeah, I'll make
You
it
have to
result.
append result directly. Result first three of result.
Yeah, I got it like this.
But then how are you going to get the first index of it? Where you
First,
hit that as a substring.
here you will get, see, you already sorted the products, right? Now for every prefix, it will get all the words here sorted
Mhm.
in a sorted fashion. And now out of that sorted fashion, top 3 I'm taking and putting it into my suggested words.
Right, but you will have to get a proper word at the first word at that index, no?
First word at that index.
Okay. Okay, if you want, you can run it, but I think you still need something more.
Will work, right?
Let me
I
print
don't know
that.
about Python, but yeah,
Yeah,
it worked fine.
yeah, because the result will always have sorted.
Always have it. Okay.
Yeah, but it's good that you optimize
That's
it. Like
why
you
we
now
sorted it first. That
Mm-hmm.
outside sorting.
use every year. So you sorted it, and first 3 I'll pick mobile, money, and monitor.
Yeah. See, the binary search approach is exactly the way you did now. Okay. The only thing is now in this line number 8, okay, where you are actually iterating through each and every word, correct? So instead of that, if you use because this will be O of n, right, on line
This
number
approach.
8,
Okay.
or the O of, if the product's
Log
length is m, so it will
Yeah.
be a linear of that. So instead of that, if you do a binary search over there, so that will be log of m. So you will actually slightly reduce some time.
But you already sorted the products, right? In the line number 5.
Right, right. So, but now
So
he
that
has
is
to
M,
find the
right?
index. That it is outside the for loop. So that
That
will.
is so.
Uh-huh.
So you have 3 or 4 products, right? So that is N, and then when you go through the loop for the range, so the N into
Because he
N
will
or
have to go and compare the prefix. Correct. So he will stop at
yeah.
the. So if the prefix is at the very end, so he'll go for a linear search of the whole products list, right?
Mm-hmm.
And from there he can just pick a number of 3 words, whatever they are as per the prefix. That's okay, but he doesn't have to go and look for each and every. So that will still be O of n. But if you do O of m, maybe if the product's length is of size m, so if you do a binary search there, then it will be, instead of O of n, it will be O of log m, a small optimization there. So that is what actually the binary search approach is, because
So
your array is sorted, right?
out here, what is our? I just joined late. So what is our objective is to get, as we go M O, see all the elements that are coming with that first digit, second digit, third digit, or maximum, or just take the first 3 and search all the products.
Yeah, I exactly the first what you said, like first digit, second digit. So you keep on adding 111 and make a prefix.
Mm-hmm.
So, Shashank, can you go to that output a bit in that example one?
At last you will get this.
So first you'll take. So my search word is mouse, right?
Mm-hmm.
Yeah.
And the products is, I have this mobile mouse, money part, and monitor. So I'll take M and I'll go through. Okay, all are valid, right? Then I take O, MO,
Mm-hmm.
and when I take MO, then I have all are still valid, right? And then
So
I
you will
take
take only the first 3 and
MOU,
sorted order.
yeah. Then I take MOU, then only I have mouse, one mouse and mouse pad.
for this much and entirely matches.
Yeah. So whenever you're returning that
Yeah.
output list, it has to be sorted always.
Exactly.
Okay.
That also has to be sorted. Yeah.
Okay. Got it. Got it.
So that will be slight optimization. So that will be the binary search way of implementing.
Actually, this is the same implementation that is used by, I think, Google search. When you type something wrong, right? If you type auto
That's
suggest,
true,
like,
but
do you mean this?
Mhm.
So basically, they have this in the mouse, right? MOUSE, So they even have all the um, wrong digits in that products list. So when you type the search word, it will suggest you. Do you mean to say, like how even in the Word document, right? When you type something wrong, it will suggest you. It already has that bad, most frequently bad used words, so they add it when they actually meant to do this,
Yeah.
and
Yeah,
then they'll suggest you.
nowadays they use advanced NLP, I mean, to do all those things, auto correction, auto suggestion, all this. I
Yeah,
think
but
back,
this is the logic, right? Kind
Yeah.
of.
yeah,
Basic logic. Yeah.
there you have BERT and all those things.
Yeah, but in the bot also, it's also Python program, right? And
Yeah, Python is a
they
wrapper,
also,
but
they might
it is
be using the same kind of
C plus
logic.
Java, C plus plus, I think.
Yeah,
Mm-hmm.
but
Python
for loop
script.
logic should be same.
Yeah.
Yeah.
Logic should be same. Yeah. So I'll quickly show you the binary search way. Okay. And then so it's just one. Okay, so this is that binary search I was talking. You can use a lower bound also. So what you did was the same, right? So you did a sorting over here, correct? So I'm using this prefix string over here, and this is my search word size M, and this is where I start the for loop or while loop, and these are my left and right for my binary search. Okay, so they will always be constant. They are based on the index of for my products. So I come here and then search, this is the prefix, and then I go do this binary search traversal here with the products LR and the target. Okay, so whatever the first three words, okay, or the minimum of if I'm at the end of the list. So I just pick them up, and every time when I pick, I still compare if the target or the prefix actually matches with the start of the word. Then only I put. So this is a simple binary search. It's like the lower bounds only. Okay. So here actually I go and look for the string. The target is a string in this case, that's the prefix. And each and every prefix of each and every word I have to compare and see if it is lesser than that. If it is not, then I actually move my left pointer, or else I move my right. Yeah. So the normal binary search, right? Yeah. So you can use lower bound also, but I just wanted to play with that. So lower bound would be an easier way to do, right?
My leftmost bound is not having three words with that prefix, then this will fail.
Yeah. So when you come here, if you have whatever the word it will give, so you will have an index here.
Yeah, but in this we always see that index plus three is all the prefixes are matching in that.
Mhm.
So yeah, so but then I'm taking if they are matching, and then when I come here, I just look for each and every prefix again. If there are no prefix found, then I don't push anything, it will be blank. So that check I'll have to do always when I'm picking any word. So I get an index
Oh,
in
okay,
the
okay,
binary search in the products array. I
okay.
still have to compare that, or else it will fail, right?
Mm-hmm.
Yeah. So there are a lot of words, and therefore he was actually moving towards try, and that makes more sense, right?
Mhm.
So these
Yeah.
things, these all small things is really optimized over there.
Do we have try implementation? Has anyone done it?
Yeah, I have that. Yeah, so this is one way I did. So there is one way in the, okay, so this is normal try. This is a try node. I'm getting the try node over here. This is my try class. Okay, so I'm using this an insertion over here. So I insert all the words the normal try way, and then I read. Okay. So the only not so good way I did over here is I'm actually using this try node a very different way. So
Least
this is
way.
normal children, and I'm putting a least here.
We use
So
hash mark here.
yeah, you can put anything there. That's true. But this is first of all not a good way of doing it. But I did that. It worked. Okay.
Yeah.
So you're like actually, so if you look at M, so I'll be having a very big list over here for M, A, B, C, D, right? So huge list. So, and that actually is per node in a try. So that's a heavy memory consumption, right?
Yeah.
So that
What
can,
list that represents?
so list represent like if it's like a prefix. So if I have M as a prefix, so whatever the words start with M, so that will be a part of that list. So whenever I go there, so if you look at this, the read, it becomes very lightweight. So whenever I come at the end and I see, okay, it has matched that prefix, I just read and release. So it's already ready-made there. And also when I'm inserting, I first do a sorting of the products here, right? So they are already sorted. So I don't have to sort them when I'm getting the output, right? So that is one thing. So when I sort and then put in the try, and then when I actually come back here and look for the search, then I just read all these try words. And also I don't have to compare if the prefix is the same in this case, right? So it means that when whatever I get from this node will have the same prefix. And if I don't get any word, then I just push empty. So that part actually the least is more memory space consumption. So it can be avoided, and for that you will have a slight different way to implement. So this is the normal try way, right? Yeah. So only when you do the search, see, I don't actually put in all my values over here now for the insert in the list. So, but when I come here, okay, so when I'm outside of it and I still am with the prefix, my prefix is still okay, and it's not returning any null value here. So then I come out of this and then run this helper function, which will do a DFS traversal. Okay, in a DFS traversal, it will go and find whatever are the words from that particular node. So this is that helper function here. So it does the same thing what we do for the search also. You again go to n, but then now what it's going to do is, so this is my WD, which is the prefix, right? So this prefix I will keep on appending with all the characters from A to Z one by one. And so if I hit on any of them, okay, so I go again traverse if I have a child, okay, in the try a child node. So I still go ahead and then actually I call the same function recursively for that particular node, okay, and then I update my prefix also over here with that particular character, right? So I
Are
keep
you
on,
just checking the lowercase here?
yeah, because everything is lowercase in this case. That is what the requirement was. So they are all lower cases. This one also, this one also.
Okay, if not, we can lower the digit and pass it in.
Yeah, so we'll have to actually, yeah, if it is lowercase and uppercase, then you'll have to do two for loops, one for lower,
Two
one
for-
for upper. Yeah.
Okay, got it.
Right.
Thank you.
Yeah, and then here when we come to that node and if you find it's a word, then only you push that in your result. Right. So this is almost like a sort of backtracking, because if your word, the prefix doesn't match, you'll have to remove that again. Okay. And then if your result size of greater than or equal to 3, then you stop there. And the rest of the other stuff is almost the same what was for the previous. I don't have to sort this, that is not required, because when I'm inserting, okay, so it takes care of that, right? So that is what is a good part of the try. So because you always look from A to Z, so they are always sorted, right?
Yeah.
Yeah, because in the previous implementation, I had to do that very specifically because I was inserting in the list also, and the list had to be a sorted one. right? My try is already always sorted if I always go from the left to right. But for only for that least purpose, I had to sort this output input also, the product one. So that I actually am avoiding over here. So this one, right? So this
Yeah.
is for that particular list what I was looking for. So if I remove all of that stuff, right, this one list. So if I
Yes.
remove all of that, so this becomes more easier, this implementation.
What is the time complexity for try one?
26. And
Well,
10 is
okay.
26. 26 is to the power m, right?
Okay, well, okay. See, if you look at the product size for insertion, if you take all the products, if the size of product is M, correct, and then you'll have to still go through each and every letter of the product, right? So it will be the size of each word of the product and multiplied by the product size. And 26, but is it not like when we insert, and that was very good thing, Shashank, you brought up.
But
But
branches will be 26 only at max, right? Worst case, like if there is a word with A to Z.
But
right,
that
but
26,
we
they,
don't look for 26 here at least in the insertion part. But that might be true when we look for the search. For the insertion, it is always whatever the index we get,
Length
we
of the
just make a node. So that might be just the number of letters in that products array. You can say that. So all the number
so,
of letters.
so if there is a word called ABC up to Z, then 26 will be there, right? The longest letter.
ABC.
A, B, C, E, F, G, H. There is a word called ABC up to Z. I mean, everything is
Oh,
one
okay,
continuous.
okay, okay. Yeah, then it will be 26 exactly. Yeah, that's true. So that will be a time complexity for insertion. It will be like the product size multiplied by its characters also. But if it is read, so then that becomes more because for the uh,
and
prefix read is same,
this products I dot length can go up to 2 into 10 raised to 4.
right?
So that will be our upper bound. Like not the maximum word length is 2 into 10 raised to 4.
Yeah, it is the word actually words length is 1000, and each word can be up to
Yeah.
this one, right? So
So
this
in our
multiplied by
try,
this.
can go up to
10.
this depth, 2
Yeah,
into 10 raised to 4.
it will be 2 into 10 raised to 7, I would say, right? So this is 10
Correct.
raised to 4 and 10 raised to 3.
10 raised to, there can be 10 raised to 3 branches. Oh
No, no,
yeah.
no. That is the length of the array. 10 is to sorry. Yeah, 10 is to power 3 is the length of the array, and each word length is 10 ki power 4. So overall, it will be 10 ki power 7, right?
Yeah. So therefore, if you look at the lead code time complexity of the try and the binary search, they almost come not so, it doesn't have a big difference because the binary search operates on the search word length, which is only 1000, right? But the try, you actually look at it, so much of construction time is spent, right? For searching also, you do so much of stuff. But in this case, most of the thing is only focused on the search word. So the binary search also is, if you look at the implementation of these, so binary search may be somewhere around, or maybe, yeah, 96, 98, and this guy actually 114. So they are not so much of a difference.
Well,
Yeah. So, okay. So yeah, when we are coming to read, so this was still okay, maybe products length in 2 raised to 10 raised to 7. But when we go for the helper function, then actually that is what you are talking about, Shashank, this 26 into the number of nodes that comes into picture. And frankly, I don't have a clue of how much that will go to because it will be an exponential also, right?
exactly.
Yeah.
26%.
Right. So it's slightly expensive if we are looking for the scope of problem because we are just looking at one search word and therefore it might be expensive. But if your search word is huge, then actually it gives better performance, right?
Yeah.
The try will surely give better performance. And also it's more of a generic, so you can use it for scalability and all that stuff, like what you said just about the auto suggestion and the other popular ones. So then try is always the best option, right?
Yeah. So we can just next one.
Yeah.
Next one. So this is like jump game 3, right? So we are given an array of non-negative integers array, which would be like, which are initially positioned at the start index, and when you are at the index I, you can jump from I to, I mean, the element at that particular index, or that much back you can go, right? I minus array of I. So we have to check if we can reach to any index with value 0. And notice that you cannot jump outside the array at any time. So it's like a frog jump we had, right? K steps back, K steps front, you can take.
So that was also part of jump game series, no? Or
That was a DP problem, I think.
okay.
3 possible cases you're having here. Greedy approach there also, like it was failing, and here.
Okay.
Yeah.
Yeah. So this is not required to go for a DP way.
No, no, no.
And what is the reason?
Because some of the
Just singing louder.
yeah, I mean, some test case will fail.
Okay.
Right. Let's say if you get somebody, I mean, let's say you try to take a maximum step and you hit 0 here, right? So now you can't go ahead of that, right? I mean, if you get at this index 0, value is 0, so 0 will never, 0 steps will never take you anywhere. So those are the cases where you will fail, I think. I mean, if I recall, anyone.
Right.
One way to
And
reach.
because we generally look at the first constants and see
Yeah.
if the DP is possible or not, and or if the length is also not so big, right? It is 10⁴, the array length.
Yeah.
So then,
N square will create 10⁵, it passes, right?
yeah, so that should be okay.
Yeah.
Is it not?
Yeah, 10⁵, I think it should pass.
Okay, so therefore we actually try to focus on the, maybe if it's a backtracking or a greedy approach. No, but if it's a DP, it's DP, right? You still have to explore, but
Explore all the possibilities. Yeah. Greedy should work, I don't know. But
yeah,
there are
it
cases
is.
I've seen where it failed. Yeah, yeah. I don't recall it long back it's done. So, I mean, most of the jump game problem I see greedy like creates a suspicion.
So the way I think why they say greedy is a optimum choice here is because you are given a start position, and also you are asked to look for a specific termination condition, which is value 0. Correct. So if you don't find it, then we actually, and as well as we actually go out of the array bounds, so we terminate.
Yeah.
Yeah. So maybe then, if you start from any index, the maximum ways to go is either left or right. So there you have only 2 ways, and also the array size is not so big. So even if you have 10⁴ and the 2 options, so okay, it can still grow in a level way, right? Yeah. So it may be, again, if it is 5 into 10⁴, the max it can grow is multiplied by 2. So it will be 10 into 10⁴. It may be max will be 10⁵ in this, the way we are thinking, like if you go left and right for each and every node.
Both the
So,
routes, yeah.
yeah, so still that is possible. Okay. Because we don't have to explore any other path because they are fixed paths, no? So we have to start and we either go to the left or right based on the whatever the values of that array is.
That is, yeah. And you can cache the index also once you are explored that, so that it won't.
Okay. Oh, yeah.
Yeah, yeah.
So that way you don't end up in a cycle.
You will avoid cycle.
Yeah. So that is nothing to do with the DP exploration, correct?
No idea it should. It's like, I mean, layman terms, it's like caching in DP is equivalent to visited. I mean,
Correct. No, I'm also trying to think loud. I also don't have a fixed answer for that.
So how does the example one output came 5? Like we start with index 4 and we can jump either 4 steps ahead or 4 steps behind. So
Start
we'll go
is
3 here.
Yeah, I think let's walk through the example 1 and 2 and 3 so it'll be
sure,
clear
sure.
instead
So
of
this is
discussing.
start.
Sorry. Mhm.
Start is 5, right? 0, 1. Okay, let's annotate, then it will make sense. So this is 0, 1, 2, 3, 4. We are starting from here, right?
Right.
Start.
Yeah.
Oh, why do we start? Like, how do we
Then
decide
index 5 we have to start. They mentioned
They
5.
will give us an input.
was
Yeah.
the
And this index is 5. So either you can take 5 plus 1, 6, you will reach there, right? I mean, 1 plus 5 you will do, right?
Yeah.
So
So fifth index plus 1 because 1 is a value. So you can either go to 6 or either go to 4.
yeah.
4 index or 5, 6 index. Okay.
this
So
is
now
6
you
and
are
this
6.
is 4.
Hmm.
4, where is 4? Or 4 is this one.
Yeah, the next to it, right? Yeah. Hmm.
I thought those many steps it will take. No, 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 it's at,
It's the yeah,
No,
those many steps only.
if,
So
if it,
it's a one step.
it's only 2 steps going left and right. So
Yeah.
one it is going to 6, now it is going to 4. So from 4 and 6 again it will follow 2 steps. Correct.
Uh,
hmm.
from 4 it will be 2, right? But from 6 it will be 3.
Yeah, but again it will keep on going from the 6 also because you'll have to still go to reach that index 3 where your value is 0. That's the termination condition.
No, like here from index 4. Oh
4
yeah,
to 7 you will go here. 4 plus,
4 to 1 and 6 to 4. Correct, correct.
so 7 they haven't taken, right? Either we can go backward. I mean,
Right.
4 minus 3
Yeah.
they are doing, they are going to this index.
Yeah,
Or
because
7
that
will
path
go
doesn't lead to index 3, maybe, or it goes outside the array. So they are not showing that.
okay.
There might be more paths also, but they have not disclosed because the what we have to return is just whether it is possible, and we just return true. So whatever the way we reach quickly, like maybe the first path from 5413, that itself will return true. We don't even have to go for the 56413
So I
longer
don't
path.
have to oh, so whatever index we reach, we have to keep checking whether that index is 0. If it is 0, then we return true. Otherwise, we memorize it and continue it.
Right. We don't memorize, but we just remember that cell we have already visited. We don't want to revisit it again.
Hmm.
Right. Yeah.
Avoid looping you will be avoiding.
Correct. So that becomes right. So if you look at that example 5, 4, 1, and 3, so that is a shorter path than 5, 6, 4, 1, 3. Right.
Mm-hmm.
So therefore, one thing's come to everyone's mind as like it's going to be a
BFS.
shortest path. Yeah, BFS way.
That is
So
in jump number 4, I think. Might be. I'm not sure.
What
mhm.
shortest path?
Okay.
Yeah, if you
This is,
look at this example, yeah, go ahead, Shashank. Mhm.
yeah, I mean, this is shortest path, right? Compared to this. So, like BFS comes into the brain, right? Or there could be some sequel questions will be there, I think, where they'll ask you what would be the shortest path, something like that.
Yeah. So this is what you would always think of, like when if you look at 5413, which is of 4 jumps, and if you go for 56413, which is of 5 jumps, so you will earlier terminate if you use that four jump one, right? You don't go for the 5 jump one because that is unnecessary. You don't even reach that. So it is the shortest path, finding a shortest path, and therefore BFS is the best approach for such type of problems.
So you are
Maybe
using BFS.
other also we can use. There might be other ways also to solve it, right?
Yeah, that backtracking you told that also one way. Let me see
Okay.
what is. Okay, I'm using DFA. Okay, same what BFS, DFS were saying,
Yeah,
right?
BFS and DFS both can work. Yeah, that is true.
So I'm just creating a set and initial result is false and passing the start index and the visited. I mean, that's it, right?
Hmm.
And once you enter DFS function, if this is true, then you this is already exit condition. I mean, if you already find that you have reached the end of the array. And now if this is equal to 0, array of index.
What
So
end
that
self dot res? What is this?
initially res is initially false, right? So once it becomes true, that means you don't need to go further. It's a terminating condition. It's a backtracking, you can say. This is backtracking only. Like
When you mark it as true, then okay, okay, okay.
here I'm marking as true, right?
But here only you can return no, return true. If
Mhm.
IAR of index is 0, you can return true.
Oh, here you are telling.
Line 10, she's saying that you can return true.
Yeah, there also I can do,
Yeah,
right?
that makes sense. Yeah.
So that's that we can do. And
Right.
here
So
we
DFS also works
yeah,
with backtracking, correct? Yeah.
yeah.
And there also you can use a visited array.
To see which
Backtracking, we are not doing backtracking, no?
it's not backtracking, but like somewhat similar to you can
Yeah,
see.
correct,
It's DFS calls only we are making here.
So see why I'm saying backtracking, because if we go in a path and then if that path again has many branches, so you still have to go up the stack and then again go for the other branch, right?
Mm-hmm.
You're
So
pruning at
that
this
is
part, right? If it's already visited, you will backtrack from that something.
mhm. So that will be still a backtracking.
Where are you checking? Oh, if not visited, you are not going the DFS. Okay.
Mm.
And the time complexity big of will be same for BFS and DFS.
Yeah,
It will be
often.
still O of n, right? Yeah,
Yeah, one time only a visit.
correct.
One time. Yeah, yeah, correct.
Yeah, so either we use BFS, DFS, but usually I will always get biased
Yeah,
towards BFS, looking at the
yeah.
shortest path. Yeah, at
Okay.
least I, because some people are really, they like the
Biases.
DFS very easy to
BFS
implement.
will also work, no? Here.
Sorry?
BFS will work as well, right?
Yeah, BFS also work. Yeah, BFS, DFS both should be fine. But as he has implemented DFS, so that is what it is.
Mm-hmm.
So you can use both of them.
Mhm.
Well, so this, I think
Yeah,
this is a more easier problem in the jump game series, correct?
Yeah, yeah, yeah.
Right, yeah.
still 4, 5, 6 is left. No, no, what is that?
At least till up till now, this was an easier one.
Yeah, because the other jump games had those game theory and all that.
Hmm.
Up to that min max optimization.
Hmm.
Yeah. Shall we move to next, or you want to share Santosh BFS one?
Yeah, I can share.
Sure.
It's not a very different what you are doing. It's just the
Almost.
BFS play. Yeah. Okay. Yeah. So I did not do any other than BFS. So this is my visit array. This is my queue. So initially I push my start in the queue and then just go in this while loop looking for this queue is not empty. Pop it from the queue and then just mark it visit. And as soon as if I find any of that, now this current will be my index. So if I look at that array, if it is equal to 0, I return true, or else I actually go for the next one. The next one is the current plus array of current. What is the value of it? Or so this will actually take me to the right side, and this y will take me to the left side. So both of them I look for if they are within the bounds of that array, right? So here I look for less than n, and this I look for greater than or equal to 0 because I'm subtracting here. And if they are not already visited, push in that queue. Same thing I do for here also, and then keep going in that while loop till I either come here where I satisfy my condition, or else I'll come at the end when my queue is empty and return false. Right. So it's a simple, straightforward BFS.
How are you taking care of out of bound condition?
Well, it is here, right? So when I actually calculate the index, the next index, so this will be my index for the right side, right? Because I'm adding one.
Oh,
And
greater than zero and
yeah.
okay.
So if I'm going to the left, I will always check because I'm subtracting this value.
Mm-hmm.
So I'll check if it is greater than or equal to 0. Then only I push that, or else I just ignore it. Same thing I'll do for the right. If it is, I'm adding it. So if I'm going to the right, if it is less than n, then only I add, or I again ignore it. So if I ignore it, then my queue will start becoming, it will shrink in size always. And then nothing will be there. And if I don't reach the termination condition, I'll return false.
Okay.
Yeah. So
Yeah, let's
next,
move to the next one. Yeah.
minimum absolute difference in BST. BST is given with non-negative values. Find the minimum absolute difference between any value of two nodes. So like three between any values of two nodes. Okay. Between 2 and 3, right? That will give you the minimum difference. 3 and 1 will give you 2.
Well, okay. So in this case, it is not always the adjacent nodes, right?
No,
You
but you
can you not? So you can have some place uh, where, or maybe some tree where you'll have to look for its ancestor. That value might be that it might be a shorter value, right?
No,
like this
actually,
6 to
it's
5.
a binary search tree. So if we do the in order traversal,
You will search for this.
then we'll get the sorted value. So any adjacent value will be the
That also true. Right.
Right,
I
but
mean,
that is
if you do
correct.
in order traversal on
Hmm.
BST,
Yeah.
then
So
adjacent
this
values.
is an example what Shashank you are sharing, right? 625. Yeah. So it's not like, because when I was looking at this input, the example, whatever they are given in the lead code, I always thought I just have to look for its parent, but that's not the case. If you look at what Shashank is showing on his screen, 625. So five's parent is 2 actually. So their difference is
Yeah.
only 3. But the real difference should be 1, which is between 6 and 5.
6, 5. Yeah.
Yeah. And therefore, what Dipali said, like if we do a in order way, so if we just, then we can actually look for the adjacent values, right?
yeah, and see, get the minimum difference out of it.
Hmm. That makes sense. Yeah.
So this is what happening here. Like
And why we can do in order search, and then you will get
because
all that.
sorted it will give them on BST in order.
So because it is binary search, right?
Just, yeah,
Yeah, that is the only reason it will give us.
yeah. Yeah.
Why are you sorting it again? It's already sorted, right?
I don't know what I'm using, right? Maybe I'm not using in order traversal.
Oh yeah, you
So
are
he is
not.
not in using in order, I think, right?
Yeah, you are using pre-order.
Pre-order, yeah.
Pre-order, yes. No,
So
but
yeah, so you can do that way also, the pre-order way.
in order makes more sense here, right? It's unnecessary. I'm doing the work. These things.
And again, with the in order will get O of n.
Both will go open.
No, no, no. We don't have to sort in case of O of in order. It will
Okay.
always be sorted in order traversal of binary search tree.
Exactly. Yeah, that's a
You
good
don't
point.
have
Yeah,
to.
because we have to take the advantage of binary search tree, right?
Yeah.
I mean,
So why we will go, see, even if you do it, that's fine, everything will go fine, but still your interviewer would try to push you towards that solution because it's a binary search tree. So that those things at least we have to, you know, come
I'll
to
avoid these lines also if
bring
I
up
use
all
it.
these things, right? Hmm.
Yeah. And
So you have
on
to
the
start with, if you don't get anything, so at least this is one solution for sure.
Yeah.
Absolutely, it could work, no issues. But still, again, we'll have to go and because that's very small thing, you know, it's not a big deal. In fact, if you can do this, then you can do in order also, right?
yeah.
Yeah.
Like we can actually avoid storing the values. Like we could save the space here.
Exactly, on the fly itself, you are saying, right? I mean, calculate the
Yeah,
difference.
like when doing the in order itself, we can just keep track of a global variable, or maybe we can use it in a function itself, and use that to store the last value that I have reached.
Reached in
Okay, the
orders.
previous value, right?
Yeah,
Makes
then
sense.
we can avoid like storing it. Like we could space, we could reduce the space. It would be just big of n time and big of one space.
So two pointers you'd be running, one previous and next always, right?
No, not the pointer. Just I'm
I mean,
storing a variable. It would just keep track of the last value that I visited. That's it.
last. Yeah.
He's saying still you go through the in order.
Yeah.
Yeah, absolutely. Yeah, and then you are actually avoiding the space, and runtime complexity is also efficient. Yeah, that will be the most optimal way of doing this.
That implementation, the in place one, the previous variable one.
Yeah,
Divyansh, do you have implementation?
I have it with me. Like just a minute.
do you want
Sure,
to
sure.
share it, Divansh?
I
You can
could
share
share
it.
it.
Sure, go ahead.
Sure. Even Maurice traversal,
Is
Morris
my screen
traversal
visible?
should not, right?
it shouldn't,
What is Morris traversal?
like no offend you can do. I mean, without any extra space, right?
Morris traversal, whenever you are doing in order traversal, you can tweak that in order traversal tree. Actually, if it's a tree way implemented,
Hmm.
and then you can point the right one. Okay, let's go to the solution first. Yeah, yeah, go ahead.
This in order three function is what I'm saying.
Mhm.
Like when I'm keeping this variable, ignore this thing.
Mhm.
Ignore it. Or just look at this function. Like when I'm doing the in order, I'm doing the same in order itself. But initially, when let's say I'm at the root, then I don't have any last value. So I'm putting it as int main. So I'm saying when I reach a node, I'm just checking if my last value is int main. That means this is my root only. So put my last value as root value. And else, what I'm doing when I'm reaching a node, I'm just checking it with my previous last value that was visited and updating it in my answer and updating this last value also to the current value.
Hmm. Yeah, that's perfect.
It makes sense. Yeah.
So ANS2 has the minimum answer.
Yeah.
Yeah.
Minus last two, and then you update your last val to root val. Okay.
Yeah. Look, basically, what I'm when I visit a node, I'm saying that because it would already have visited a node itself when I'm doing the in order. So I'm checking here that last value and my current value is this root val, and I'm checking that whether is this minimum to the ANS that I've already stored. And ANF I've initiated with int max, so
Hmm.
we could update it. And when I'm done with this node, like I've checked for this one, then the last value would be the current value only, so that I can use it for this.
Yeah. So every time you are actually updating the last value,
Yeah, that's
irrespective of it. Yeah.
Yeah. Can you post this solution on Discord?
I will
Yeah, you can actually whatever the ones which you think is the only one, you just remove that, and whenever you have time, maybe today you can just post it on the Discord channel, the same channel what we, yeah, just the optimum one. Yeah. Not on the chat, you can actually post in Discord, so it will be useful for anyone else who wants to look at it later.
sure.
Yeah, thank you. Yeah. So this was okay. So the Morris traversal, actually it modifies your tree. So because usually your tree will have left and right branches, right? So in cases when you are going to the left side, and if you happen to have another branch on the right also, so you can actually go to the rightmost part, and the very right which has a leaf, which is leaf, so its right will be always null, right? So you can actually use that to jump back to a previous parent, so you'll have to make some modification in the tree structure there, and then you keep on doing that traversal, and so when you are coming back in your stack again, you'll have to revert those changes. So it is slightly a different way of doing. So there you actually avoid using. But now what are we going to avoid in this case? Because we are actually avoiding the space also, right?
Yeah.
So
Or
in
no.
fact, this will be a better option than the Morris traversal, is it not?
Yeah, but there then can't we avoid that space? I mean, O of n. I mean, rather than storing the
But I
value
think for
like
this particular problem, whatever uh, Devansh has shown, right? So
yeah,
that should be the best approach, I would say.
yeah. He's of constant space also is taking, right?
Yeah,
Yeah.
yeah, it is only one
What's
variable.
the application of Morris traversal?
Yeah, Morris traversal is when we actually traverse a tree using in order most of the time, right? So, but then I think the best part is actually you do everything in O of one,
Oh, okay,
base
okay.
complexity, something like that. Yeah, we'll have to look back. I'm not very sure though, but it's very efficient and it's not a very difficult algorithm also. But you'll have to be focused and look at it, and then you'll come to know it's not difficult.
Hmm. Yeah, it's there on Geeks or for Geeks. I'll
Right,
post.
right.
I'll post.
No problem.
Okay, so that we
Okay.
can
So did you stop the recording?
learn from that. Yeah. Don't post here. It will go okay. You have posted.
She just posted the gigs for gigs. Okay, that's fine.
Yeah.
Yeah. So okay. So he talks about